The double-slit experiment is so exciting to physicists and so interesting to everyone interested in quantum mechanics because it contains the essence of quantum mechanics.
In the double-slit experiment, a beam of electrons strikes a baffle with two narrow parallel slits in it, and then a screen.
When we do this experiment with the lights on, nothing unusual happens. The electrons form the same pattern on the screen that you would expect for spitballs or wads of gum or even tomatoes. But when we turn the lights off, something very surprising happens.
What one observes on the screen is a series of maxima and minima.
This series of maxima and minima is known as an interference pattern.
Maxima are places where electrons accumulate. Minima are places that they avoid. The interference pattern is what you'd expect to see if you sent waves, not particles, through the double slit.
What we observe in the double slit experiment is explained mathematically by Schrödinger's wave equation, which predicts exactly the observed interference pattern. But quantum theory doesn't tell us where the particle is as it goes through the slits.
The essential difference between classical and quantum physics is that in classical physics one can predict both the positions and the velocities of particles, whereas in quantum theory one can't predict either.
Why is the pattern on the screen different, depending on whether the lights are on or off?
In classical physics, we are used to the universe which is independent of us knowing about it or not. We can look at it, but whatever it does doesn't change. It doesn't care. It runs according to its own rules. This is no longer the case in quantum mechanics. They're looking at something, making an observation of it, changes how it behaves.